We've talked about inverse sine, inverse cosine, and inverse tangent already, but we did so from the perspective of the graphs of the functions. We looked at the graph of sine, and then we looked at the graph of the inverse sine. We saw how if we rotate the graph y equals the sine of x around the line y equals x, we end up with the graph of y equals the inverse sine of x. That's how inverses work, graphically speaking. But we had to restrict the domain because the graph of y equals the sine of x failed the horizontal line test, which means that the graph of the inverse sine, if we hadn't restricted the domain, would have failed the vertical line test and it wouldn't have been a function. So in this video, we're going to be looking at the inverse sine, cosine, and tangent functions again, but this time we're going to be doing that from a more algebraic perspective. I'll assume that you already know and understand that the domains of sine, cosine, and tangent have to be restricted if we're going to be dealing with their inverses. Let's put a quick reminder on the screen about what those restrictions are. If y equals the sine of x, we have to restrict the domain of x, the domain of the function, the values of x, to values between negative pi over 2 and pi over 2 in order to be able to talk about the inverse of sine. This domain restriction includes the endpoints, so we can actually use the value negative pi over 2 and pi over 2. The tangent of x has the same domain restrictions, except that we cannot use those exact values at either end of the interval. The cosine of x has to have its domain restricted to 0 to pi, including 0 and including pi, if we're going to be allowed to talk about its inverse function. Now, we looked at the graphs of these functions already, but what we haven't done is actually used any of them. Let's take a look at an example using a right triangle. If I know the measurement of this angle, let's call it pi over 6, and I know the measurement of the length of one side, then I've already been able to solve problems like this. Like, let's say I wanted to know, what is x? What is the length of the hypotenuse of this triangle? Well, I know that the sine of pi over 6 is, because the definition of sine is opposite over hypotenuse, I know that that's going to be 3 over x. And then solving for x, I get 3 over the sine of pi over 6. Well, the sine of pi over 6 is a half, and 3 divided by a half is the same as 3 times 2. So I've been able to solve problems like that before. What I haven't been able to do is, if I know the lengths of the two sides here, find the angle. Let's do one of those. All right, so in this example, I know the lengths of two sides of a right triangle. I know it's a right triangle because of this mark in the corner, and I know the lengths of two sides, and I know there's an angle whose measurement I don't know, but I still know that the sine of an angle is equal to the length of the side opposite that angle over the hypotenuse of the triangle. Now in this case, I happen to know that the angle whose sine is the square root of 3 over 2 is pi over 3. I know that, but let's talk about how you could figure that out, at least numerically, as a decimal, if you didn't know that fact, because there will be many times when the sides of the triangles that you'll be given won't lend themselves to a value that's just in a table that you can look up or something you have memorized. So let's talk through the analysis of what's going on with sines and angles, and if I'm looking for an angle instead of looking for a side, let's copy this sine equals, sine of phi equals, and I'm going to give myself a little bit of space here, the square root of 3 over 2, and then I'm going to do the same thing to both sides. I'm going to take the sine inverse of both sides. On the left-hand side, I have the sine inverse of the sine of phi, okay? And as long as, because I'm working with sine, as long as phi is somewhere between negative pi over 2 and pi over 2, I can say that's just phi. I don't actually know that phi is somewhere between negative pi over 2 and pi over 2, except that I kind of do, because phi is in this right triangle in this particular instance, right? I'm working with right triangle trigonometry now. And so since this angle is 90 degrees, the very largest that this could possibly be would be 89.999 degrees, right? This is pi over 2, so the very largest that this could be is just under pi over 2, just under 90 degrees, because there's a third angle here, and unless that angle is 0, this can't be pi over 2. It can't be exactly 90 degrees unless this angle is 0, in which case we don't really have a triangle. We certainly wouldn't have two different sides here. So because I know that this angle is 90, this one must be less than 90. Therefore, I know that I'm in the right domain for sine to use sine inverse, and so I can get away with this. And now I can ask myself, sine inverse of root 3 over 2, what is the angle whose sine is root 3 over 2? And the answer to that question is pi over 3. Now that's pretty much what we just did before, but I'm showing you this. You can take the sine inverse of both sides to sort of, I don't want to say prove, that's too strong, but sort of demonstrate what's actually happening when you solve this kind of a problem, right? You know the sine of some angle is root 3 over 2, and you're looking for the angle. We haven't done that before. All right, I'd like to do another example, but this time I'm going to give you a value for the sine of the angle, this value right here, that's not in your table, and we'll see how we deal with that. Okay, here's my new triangle. I have an angle labeled. Now I might have labeled this one as well, but I just tried to keep it as simple as possible. So for this angle, I know that the side opposite that angle is 3, and I know the side adjacent to that angle is 7. So thinking about which trigonometric ratios use opposite and adjacent, I can either say that the tangent of theta is opposite over adjacent, 3 over 7, or that the cotangent of theta is adjacent over opposite, 7 over 3. Now, that's not in my table. 3 over 7 and 7 over 3 are not values I can find in my table so that I can go back and figure out what that angle is. So I'm going to have to use a calculator. And because tangent is already a button on your calculator and cotangent is not, I'm going to propose that we use tangent. This is pretty common. By and large, we use the three trigonometric functions sine, cosine, and tangent vastly more often than we do cotangent, secant, and cosecant. Those other ones do come up, and it's important that we're familiar with them and comfortable with them. You're going to see them again throughout the course. But for an example like this, let's just use tangent. It's the easiest option. All right, so if I know that the tangent is 3 over 7, then, and I'll just go ahead and copy that down again, tangent of theta is 3 over 7, and then I'll take the inverse tangent, or the arctangent of both sides. I'm just using this notation. I can't quite squeeze that in there. Let me move my 3 over 7. I'm just using this notation because I want to use them both. I want to use inverse notation and arc sine, arc cosine, and so on. I want to use both kinds of notation so that we are familiar with both. All right, now I've taken on this side the arctangent of the tangent of an angle, right? And again, I know, where's my tangent? I know that my angle is somewhere between negative pi over 2 and pi over 2 because this angle is pi over 2. That means the total of these two angles, because I'm in a triangle, have to add up to pi over 2, or 90 degrees. Pi over 2, if one of them is 0, then the other one is pi over 2, but then we're not in a situation where two of the sides can be 3 and 7. So this one must be greater than 0, so I'm not right up at my, it's not the case like with sine where I'm right up at my extreme value pi over 2. I'm not allowed to use pi over 2, but that's okay. I don't need it. So this angle is something less than pi over 2. It has to be. That means that on the left-hand side, I can get away with saying, well, that's just theta. Now, for the other side, I'm going to have to use my calculator. If I type in second tangent, that gives me the tangent inverse function. So there's the second button and then the tangent button, and that opens a set of parentheses for me. And I'll type then 3 divided by 7, and I'll close the parentheses, and I hit enter. And when I do that, I get a decimal number that is approximately, because I'm only getting, let's see, 5 decimal places on my calculator, but that's still not the exact value. I get 0.404891786.3. And depending on your application and your instructions, it probably suffices to round that to 3 or 4 decimal places. So that's how you solve those. Now, here's something to keep in mind. When I did this problem, my calculator was in radians. So I found an angle in radians. If I do the same problem in degrees, I get 23.19, I'll go to 4 decimal places again, 1986. And I have to use a degree symbol because otherwise that looks like it's in radians. Unless there's a degree symbol there, I'm going to interpret this as being in radians. This one does not have a degree symbol, so it's in radians. My calculator was in radians. I didn't have to do anything different to get the degrees. I just had to re-enter the problem, tan inverse of 3 over 7, but my calculator had to be in degree mode. The vast majority of the time, I'm going to ask you to be working in radians, but occasionally something will come up and the question will be asked in degrees, or the answer will be expected or required in degrees. So it's useful to know that you can do a problem like this simply by checking the mode on your calculator. All right, that's all I'm going to do for this video because the vast majority of the rest of this topic we've already covered. We've talked about the domain restrictions. We've talked about how to find inverse trigonometric functions on a calculator. We know about the inverse sine, inverse cosine, and inverse tangent graphs, although those aren't actually mentioned in this topic. They came from chapter 6. So we've already covered most of this. So I'm just going to keep this one nice and short, and we'll go on to the next topic, which is solving for right angles and right triangles. Now, actually, we've already done one of these. This is the sort of the most basic. We've actually done two. The very most basic type of problem where you might see this type of thing asked. A lot of the problems that you'll see like this are actually applications. So we'll be talking about some applications in the next topic.